Yes, so this talk is going to be about why approximating constraint satisfaction problem requires huge LPs. There was some debate about how huge it is, and it was sub-exponential versus weakly exponential. And I think Avi is probably the reason why it's weakly exponential right now instead of sub-exponential. It's like some terminology difference. But we're going to see what it means in a moment in symbols, so it will be clear. There's also one other point I want to make before I begin. Like if you check the title of the paper, it's a union of two titles. Like there is half of the part which I have not included here, and it's like depending on which one of us is giving the talk, we use one part of the title. It's because like, the other part is more communication complexity oriented. This part is more CSP or like approximation oriented. Anyway, so this is based on joint work with Raghu and Prasad. So let me start by telling you the results. So the main result of this talk is going to be that there is some constant delta naught, such that if you take a 2 to the n to the delta naught size linear program, then such a linear program for the max cut problem will have a gap of factor 2, for 2 sat a gap of 4/3, for 3 sat a gap of 8/7. And if these numbers sort of are weird looking to you, let me clear away the mystery. These are basically the approximation ratios achieved by the simple algorithm that simply returns a random assignment. Okay? So if you return a random cut, it's a half approximate algorithm, and basically this result is saying that even if you use a 2 to the n to the delta naught size linear program, you cannot beat the guarantees given to you by simply returning a random cut. Okay? And in some sense these are just corollaries or examples of the lower bounds we prove. Basically we can prove any lower bound that can fall out of this technique, so I'll explain this in a moment. But basically the idea is that we're going to show that if you take any 2 to the n to the constant size linear program, then such a linear program for approximating CSPs is no more powerful than a similar size specific linear program known as the Sherali Adams linear program. Okay? So the Sherali Adams linear program is a very specific explicit linear program that people understand very, very well. I'm going to tell you some of these results in a moment. And basically the main result of this talk is to say that you can write an arbitrary LP and it's not going to be more powerful than a similar size Sherali Adams LP. And then you just compose it with the known Sherali Adams lower bounds to get all these corollaries out. Okay?
But arbitrary LP is restricted in some sense.
Yes.
Because of the, you can imagine like very fancy reductions.
Yes, yes. So Ran is making a great point. So I'm lying on this slide a little bit, and I'm going to clear away that lie in a moment. But bear with me with this inaccurate statement just for this slide. Okay. So just to sort of make this point precise, this relationship was first sort of noticed, and in fact that's the main punch of this really great paper of Chan, Lee, Raghavendra, and David. And they basically showed that any n to the log n size linear program is no more powerful than a similar size Sherali Adams linear program. The issue of course was that their technique broke down to show this connection between any LPs larger than n to the log n in size. And what we are giving today is a exponential strengthening of the result of CLRS. Okay? And again we will touch upon this topic also. There is a reason why the technique of CLRS would break down. There is a necessary, in some sense the technique is doomed to go beyond n to the log n. And the reason we can go beyond n to the log n and get sub-exponential or weakly exponential lower bounds is because of this sort of a new way to prove linear programming lower bounds by connecting them to something which is studied in communication complexity. So in particular we are going to establish a tight bound on the non-negative rank of something called as a pattern matrix. Okay? And many of the terms, maybe all of the terms on this slide might appear foreign right now, and it is not completely clear because I have not defined them. But think of this as an extended title slide. Okay? I just wanted to tell you what's sort of going to happen in this talk before I tell you the details. Okay? So before I go on to answer Ran's question and what it means to say an arbitrary LP, let me first tell you a little bit about history so that we can place all these results in context. Okay? So linear programming lower bounds is by no means a new endeavor. It's been going on for like a long time. And in the beginning, people were trying to linear programming is a very versatile tool for algorithm design. So in the beginning, people would come up with LPs and try to analyze them. And one way to sort of understand what's the best approximation algorithm you can get out of a certain LP is to prove an integrality gap lower bound on it. try to basically nail down the best approximation ratio you could potentially get from the LP. And if it's not good enough, then you might want to write a different relaxation, right? But on a systematic, so this sort of endeavor was put on a systematic footing by trying to understand a class of linear programs all at once in the seminal work of Aurora, Bolobas, and Lovash. And since then, basically, this area has exploded, and we now understand many specific linear programming hierarchies. We completely understand how they behave on many important problems. In particular, for CSPs, in some sense, all these results, the details are not relevant. All these results basically are saying that the picture for many of these specific linear programming hierarchies, in fact, all of them, I think, is essentially clear for solving constraint satisfaction problems. Okay. And arguably, the ultimate goal of such a endeavor would be to prove a lower bound against an arbitrary linear program. Again, there is some conditions apply on this arbitrary. I'm going to explain in a moment. This model itself, again, is not a new thing at all. It was introduced in the seminal work of Yannakakis from 1988. In the same paper, he defined what it means to say a lower bound against an arbitrary linear program. This was conceptualized as the idea of linear extended formulations. Then he also showed a relationship to a simple analytic quantity related to the problem at hand, which is called as a non-negative rank. And he showed an exponential lower bound on symmetric linear programs for solving maximum matching. And in some sense, like symmetric linear program is basically a linear program that shares the symmetry of the matching problem. So Yannakakis in his paper asked that the symmetry shouldn't be a really important assumption to prove a lower bound, although his technique didn't give a way to sort of go beyond it. And it took 24 years to basically resolve, or at least go beyond this symmetry condition that Yannakakis put in this breakthrough work of Fiorani, Massart, Pokuta, Tivari, and DeWolf from 2012. And they showed a sub-exponential lower bound for traveling salesman problem, like 2 to the root 10 size lower bound. And since then, again, this in the last 4 years or so, a lot of extremely interesting work has been done in this area of understanding extended formulations for various problems. And in particular, following this, this framework was generalized to approximation problem instead of exact problems by Braun, Fiorani, Pokuta, and David. And then they showed a lower bound for approximating clique, which was tightened to the right answer by Mark and Ankur. And okay, and since then, basically, a number of results have been known. I don't want to mention all of them in detail, but basically, the point is that we understand many things very well about extended formulations now than like 4 years ago. Okay, great. So, and yeah, this work is going to be about weakly exponential lower bound for CSPs. We are going to stand on the shoulders of all these giants that came before us. Okay, so let's answer Ran's question. In some sense, it's important to understand what you could potentially prove a lower bound on, because as Ran mentioned, you know, if P is equal to NP, which we can't refute right now, then there might be some crazy reduction from the CSP problem to, let's say, the bipartite matching problem, whence you could write some LP for bipartite matching and solve your CSP with an LP. I can't potentially prove a lower bound against that LP that you could write. So clearly, I have to restrict my model somehow in order to make sense of a lower bound here, without sort of going, you know, without trying to touch the P versus NP question. So let's see what would I mean by an arbitrary LP for CSPs now. So let me first introduce the standard relaxation, and throughout I'm going to think of max cut as a running example, although you will see that things are very general and they apply to all CSPs. It's just convenient to stick to a notation and single problem for the purpose of definitions. Okay, so we all know the max cut problem. We want to find something that maximizes this normalized cut, and we're going to write opt of G for the maximum, the size of the maximum cut in graph G. Great. So by basically thinking of x as the indicator vector of a set, this is same as maximizing a sum over the edges 1 minus xi xj over 2, and this is basically just the indicator of whether edge ij is included in the cut defined by x or not. So this is a 0 1 valued function that tells you it gives the value 1 if ij is included in the cut. So what we're going to do, well, the first issue we have, so linear programming is like trying to maximize or minimize a linear function over a polytope. We would really want to maximize this function, which is not linear, so we're going to linearize it. We're going to introduce variables yij for this indicator. Okay, so yij would stand for this quantity, And now once we have this, we can linearize the objective as just maximizing yij's, right? And now we want to sort of enforce constraints that all true solutions will be subjected to. We want to add some constraints on y's such that the y's obtained from our intended solutions should satisfy all those constraints, right? So basically this is going to be done by adding some restricting yi to lie in some polytope. And so for example, what I would call a standard relaxation for max cut would look like this. You know that this indicator was 0 or 1 valued, so I relax it to an interval. I say that in a triangle I can only pick 2 edges in a cut. In like a 5 cycle I can pick only 4 edges of the cut, and so on, right? So I add basically whatever seems reasonable for the max cut question. This for example is one way to obtain a relaxation for the max cut problem. And my goal to show you is that this sort of can now be generalized to see what I mean by an arbitrary LP. So what did we do on the previous slide? Basically we took, so this is in some sense the most general version I imagine as an arbitrary LP. We take some number m much larger than n. N was basically where this cut naturally lived in. X was a vector in +1 -1 to the n. So we take some higher dimensions m. We map every graph into a vector in Rm. Okay, so now I make every graph into some vector in some higher dimension. Similarly, I make cut a vector in the same space. And the only restriction on choosing this map from graphs and cuts into vectors is that the map should be sensible, in that if I compute the inner product of Vg and Ys for any graph G and any cut S, then it should really just give me the value of the cut in the graph G defined by the vertices S. Okay. In other words, this should be like a meaningful linearization. Okay. And I allow, subject to the constraint that you compute the cut value over all graphs G and over all sets S, I allow any possible linearization. Okay. Now in the next step in the standard relaxation, we introduced a polytope to constrain our linearized vectors corresponding to cuts in, right? So we wrote this y variables for the cut for sort of parameterizing the cut, and then we restricted y to some polytope. We're going to generalize that here now. So we're going to say that I can add any linear constraint that is valid for ys obtained from every possible cut s. So whatever is valid for all true solutions, which is the space of all cuts, I take the linearization, and I can add any set of linear inequalities that are valid for all the linearized versions of the cut obtained under this linearization. Okay. And basically my LP is then defined by this linearization, the choice of maps of graphs and cuts into vectors, and the polytope P that I chose to constrain the y vectors in. Okay, and that's my LP. In particular, let me point out what kind of LPs I'm not allowing. Okay, I could potentially take the graph G, right, and pre-process it, compute some quantity about it, and then write an LP where the constraint depends on what I computed from the graph G. This is an LP which is not captured in this model. Okay, the polytope is a function of only the feasible space, which is the space of all cuts. I do not allow it to depend on the graph, the instance that I'm given. The objective is where the graph appears. So objective is the only place where the graph would appear. Okay, so that's in some sense the only restriction that I'm actually placing on when saying we are going to prove lower bound against arbitrary LPs. Great. So the value of this LP is just the natural thing, the maximum over this polytope P of the inner product Vg and y. And size is going to be is basically this m is not important. Just think of it as the number of inequalities in this polytope P. Okay, so all fairly standard stuff. And now I want a method to measure the performance of my LP. So I would say that this LP achieves the C comma S approximation if whenever the optimum of a graph G of an instance G is at most small s, the LP returns a value which is at most small c. Okay. Now we chose a valid relaxation. The linearizations of all possible solutions were always included in our polytope. So this c cannot be less than s. Okay. And really, like so the closer c is to s, the better the LP in some sense. Right. Okay. Great. So that's That's what linear program for CSP or max cut problem means to us. And now you could imagine, this seems like a fairly general model. I don't have a handle on the linearization, or I don't have a handle on the polytopy, and I'm still supposed to prove a lower bound against it. How can I sort of accomplish this? And this was sort of made super simple, or at least made tractable in this early work of Yannakakis that I mentioned before. Okay, and he characterized this. So in some sense, the issue is this, right? Like, given a problem, I can choose many linearizations and many polytopes, and in some sense I'm trying to prove a lower bound against all of those things. What would be really nice is if I could come up with a characterization of the best LP's size for a given approximation that depends only on the problem. So here, for example, the max cut thing. Okay, and Yannakakis basically gave us such a quantity. So I'm going to tell you what that quantity is now. Okay, so basically I'm going to form this matrix which I'm going to call M cut. Okay, this is the matrix whose rows are indexed by all possible instances G, such that the optimum max cut value of G is at most small s. Okay, so the C and S are fixed now. So I'm trying to look at LPs that achieve CS approximation. Okay, so I have rows which are indexed by all instances with optimum at most small s, and the columns are going to be indexed by all possible solutions, the cuts. Okay, and the G comma Sth entry of this matrix is going to be C minus the cut value in the graph G of the cut defined by the vertices in S. Okay, in particular, notice that we said C is always larger than S, which means that cut G of S is always smaller than C, which means that this quantity is always non-negative. In particular, this is a non-negative matrix. Okay, what Yannakakis showed, or at least some version of what he showed, is that if there is a CS approximating linear programming relaxation for the max cut problem, then this matrix has a quantity called as a non-negative rank at most theta of R. Okay, and this is actually an if and only if, but I only want to state one direction because that's useful to us today. Okay, he basically completely characterized it. So just to restate, basically the non-negative rank of this matrix is up to constant factors a tight estimate of the best linear programming size for obtaining C comma S approximation for the max cut problem. Okay, so what is this non-negative rank? I am pretty sure like most of you have already seen it, but let me define it nonetheless. So for a non-negative matrix, for a matrix we can define the rank as the minimum number of rank 1 matrix that I can write the matrix as a sum of, right? So all I'm going to impose is the non-negativity constraint on top of this. I'm going to say that this matrix has a non-negative matrix has non-negative rank R if R is the minimum integer such that it can be written as a sum of R non-negative rank 1 matrices. Okay, great. And in terms of this, then we have the Yannakakis characterization completely clear to us. And in particular, it says that if I wanted to understand or prove a lower bound on the linear programming size for CS approximating max cut problem, then all I need to do is prove a lower bound on the non-negative rank of this matrix. Okay, and this is some, okay, it depends on how explicit this matrix you would think it is, but at least it's completely defined by the cut problem. Okay, I don't have to now think about linearizations or polytope, etc. Anymore. Great, and in some sense this relationship is responsible for connections to communication complexity, which in some sense has been responsible for all the revolutionary kind of breakthroughs that have happened in the past 4 years in this area. Okay, so I said it's like a somewhat explicit matrix, this M cut thing, and I want to prove a lower bound in it, but it turns out that it's not that great a matrix after all in order to understand what its non-negative rank is. So in order to lower bound, what I'm going to do is find some structured sub matrix, okay, which I'm going to call a pattern matrix, and then instead prove a lower bound on this pattern matrix. Okay, so a lower bound on the non-negative rank of a sub matrix is always a lower bound on the non-negative rank of the whole matrix. Okay, the only thing is how good this is. So in some sense, I would hope that this matrix is sort of a large enough fraction of the matrix I'm looking at, and then I will hope that I get a tight bound on the non-negative rank of this matrix. Okay, but that's going to be my strategy, to come up with this pattern matrix, embed it inside the M cut matrix, and prove a lower bound on the non-negative rank of the pattern matrix. Great. So what are pattern matrices? So for the purpose of this slide, you can forget about all the M-cut things. Okay, this is just a standalone definition, and I'm going to tell you like this is a very well studied idea in communication complexity. So you have some one-party n-bit Boolean function. So sorry, I mean a function that's on the Boolean hypercube and takes real values. So by one party, I'm trying to sort of refer to the communication complexity nomenclature. So it's like a single party function. There is no communication going on in this context. You can make a communication game out of this function by introducing a two-party gadget. Okay, so gadget is basically a function that takes two inputs from some alphabet sigma and outputs a single bit. Okay. Given a two-party gadget like this and a one-party function f, I can make the communication game in the following way. Okay. So the row player gets x1 up to xn. So this n blocks of sigma. So x is indexed by x is a n length string over alphabet sigma. Y again is the input of Bob, who gets a n-bit n length string on alphabet sigma. And how do I so what's the game? What's the function I want to compute? So the function is obtained in this way. You take the first blocks of x and y, you apply the gadget g to it. So this is some element of sigma, this is some element of sigma. I apply some gadget g to it and obtain a single bit g of x1 y1, let's say z1. Similarly, I apply it to the second blocks, third blocks, so on. Okay. And then at the end, if I apply the gadgets to the corresponding pairs of strings from sigma in x and y, I get a n-bit string out. To this n-bit string, I apply f. Okay. So now you can see that the function I want to compute is a function of both Alice and Bob's input, and in some sense, I have composed this function f with the output of this gadget g. Okay, and that's basically what a pattern matrix is. Is the definition of pattern matrix clear? This is going to be really important for us as we proceed.
You want to give examples like disjointness or inner product are specific examples?
Yes. So for example, if you've seen the disjointness matrix as I was referring, then it's an example of a pattern matrix here, where let's see.
One party is an O and
yes.
And the two-party gadget is an AND of one bit.
Correct. Yes.
And otherwise, if you put parity on top, then it would be the
inner product. Okay. So those two examples might be familiar to you already. So I hope that you at least see that this is not a foreign kind of an object. It has been studied a lot, and the context that it has been studied in is in proving a lifting theorem. So what's sort of a lifting theorem? So here is sort of a meta goal in communication complexity. Okay. What you want to do is relate the communication complexity of this game that we defined on the previous slide. So computing this block composed two-party function in terms of some complexity measure of the single party function f, and the gadget g is in your control. Okay. So in other words, what you want to do is lift the hardness of this function f through some suitable gadget into getting a communication kind of hardness for the game defined by the matrix mf. Okay. That's sort of the meta goal. And there are like number of great results in this direction in communication complexity. So and in fact, this started with the work of Rahn and Mackenzie, who related deterministic communication complexity with the decision tree complexity of the function f. So if you wanted, so this is some communication measure, this is some complexity measure of the function f, and this paper gives a characterization of the deterministic communication complexity in terms of this complexity measure of the function f. Okay. And this has been sort of done for in many different communication complexity measures now, for quantum communication complexity, discrepancy, etc., etc. Okay. Again, the specific results are not important to us. The point I want to make is that relating some measure of mf to some measure of the function f is like a task that has been done many times, and we understand many sort of related aspects of this task. Okay. So coming back to our question, what do we want to do? Well, we want to understand the non-negative rank of this matrix mf, right? And we want to relate it to some complexity measure of the function f, right? For some suitable gadget g. So what complexity measure of f are we going to use is the next question. So for that, I'm going to define a non-negative D junta. Again, I'm pretty sure like most of you already seen this, but just for the sake of completeness, a Boolean function of n bits, so a function on the Boolean hypercube of n dimensions, is a non-negative D junta if it depends on at most d variables and always takes non-negative values. Okay, simple.
Yeah. So the complexity measure is d. You said you are going to define complexity measures. So
I'm defining.
Okay, good.
Yeah. So that's a non-negative D junta, and the non-negative degree. So this is the complexity measure of the function f. Okay. So for a non-negative function f, the non-negative degree of the function f is the least integer d, such that f can be written as a non-negative linear combination of non-negative D juntas. Okay. And if that looks somewhat weird, let me just relate it to something that you are all aware of. Okay. So I can define the polynomial degree of the function f as the least integer d, such that f can be written as a linear combination of D juntas, because the monomial functions, the D length monomials are just juntas, right. So in particular, the polynomial degree is relates to linear combinations of monomials. I can always make the monomials non-negative by, like, for example, choosing the conjunctions as my monomials, etc. So the only difference here is that now I am allowing you to only take non-negative combinations. Okay, this is reasonable to ask because my function f is non-negative. So it's not like I have to produce some negative values anywhere. I'm asking what's the best representation of f as a non-negative linear combination of non-negative D juntas. Okay. And it should sort of remind you of this non-negative rank that we did before, right. This is like similar what we did for matrices. For matrices, rank decomposition is the minimum number of rank 1 matrices that sum up to the matrix M. Then you pose the non-negativity condition on them to define non-negative rank. This is similar. For a function f, from degree I am going to non-negative degree. Okay. And the lifting theorem that we are going to show is a relationship between non-negative degree of the function f and for a suitable gadget G, the non-negative rank of the pattern matrix MF.
So what is the advantage of taking juntas and not monomials?
They are the same. They
you could have just said it's a polynomial with non-negative.
Yes. Yes.
So why?
Yes. Yeah, you're absolutely right. It's just monomials. Somehow I thought junta was more familiar, but I suppose. Yeah. No, but they can be thought of monomials by just allowing xi and 1 minus xi as variables. It's not. Yeah, it's okay to think of monomials, I think, and it won't take away anything. Yes.
It's a bit confusing. What about polynomials which are non-negative but have negative coefficients, like some negative coefficients?
Some negative coefficients.
Yeah.
Well, so it's.
They don't allow it. The model is monotone.
No. So let's see. So this is a question about some representation for a function f. Okay. Let's say you have a function which is some some negative coefficients appear. Okay. So you have a polynomial that has some negative coefficients, but it takes non-negative values. Okay. Then I can hope. Okay. First of all, I can always write any non-negative function f over the hypercube as a non-negative linear combination of n juntas. Do you see that?
Right. I'd forgotten it was over the hypercube.
Yeah. So yeah, over the hypercube I can always write it as an n junta, and the question is how much smaller can I make it? And in some sense, if I am a degree d polynomial, then I cannot make it smaller than d. And the question is how much larger do I need to go to get?
I see. Okay.
So is that clear now?
Yeah.
Great. Okay. Great. So just to say what is the lifting theorem we are going to prove now. We are going to relate, as I said, the non-negative degree of the function f to the non-negative rank of the pattern matrix MF. Okay. So what is sort of easy to see is that the non-negative rank is always upper bounded by an exponential in the log of the alphabet size and the non-negative degree of f. Okay. And this is true for any gadget. Okay, so this is like really simple result, and the only, so let me just give you like a quick reason why this has to be true. So if f is a D junta, right? So look at any D junta, or let's look at any D monomial, right? If I apply the monomial to the output of a gadget, the whole thing is a function of at most d blocks of length sigma, d blocks over the alphabet sigma. Okay. In particular, the whole matrix is of size at most exponential in this. So all I'm saying is that if I take if I take any matrix which is non-negative, this non-negative rank cannot be more than its number of rows, which is just a trivial bound. So all you have to do to prove this is to just take each term, which is a junta, and do a trivial upper bound in terms of the size of the matrix, and that gives you this upper bound.
So another way of saying it is that every monomial is a positive rank 1 matrix.
Yes.
Okay.
Yes. That's a simpler way. Yes. But what we are going to show is that this sort of loose, what appears like a loose bound, is actually tight. Okay. So our main result is going to be the following: that if you take any function over the hypercube which is non-negative, and this is just normalization because I'm going to allow some shifts in a moment. So let's say it's normalized so that its expectation over the uniform distribution is 1. Okay. Then I said that I'm allowed to choose a gadget which is suitable to me, so I'm going to choose the inner product gadget. Okay. So my sigma is going to be b bits. Okay. And now my gadget g takes 2 b bit strings and computes the plus minus 1 valued Boolean inner product of alpha and beta. Okay. So given any function with expectation 1 and this inner product gadget, if I compute the pattern matrix, then for any b which is larger than some log n, this will come to this again later on, we are going to show that the non-negative rank of the pattern matrix is basically this quantity. So b, remember that b is the log of the size of sigma. This is the degree plus of f, except that instead of f I now have some kind of an additive shift to it. I've added some positive quantity which is like 1 over n. Okay. So notice that if I take a function and add like a positive quantity, I make it more positive. So in some sense I am reducing its non-negative degree. So the lower bound we are proving is in terms of the non-negative degree of this shifted function f. Okay. But up to this additive shift and up to some constants here, this is really the trivial upper bound that I showed you before.
In practice, in the examples that you analyzed, the additive shift really changes?
No, that's going to be the point. Like this error is tiny enough that degree plus of f and degree plus of f plus 1 over n is really going to be the same for us.
But it's for technical reasons.
Yes. Yeah. In fact, I don't know. I don't even have a conjecture of what a proof strategy will look like, which will not incur this additive shift. We'll come to that in a moment. I'll hopefully be able to explain all these things to you. Great. So that's going to be our lifting theorem, and that in some sense is the main technical core of what we're going to do today. Okay. But before going on, let me mention one sort of a subtle detail which will also clarify why the previous papers that I mentioned were not able to sort of get a lower bound which is more than quasi-polynomial, while we can. And this in some sense is this is the reason why like this going to pattern matrices is really helpful. Okay. So one can sort of summarize the main sort of technical core of both the Chan, Lee, Raghavendra and Stoller paper and this recent paper on communication complexity, which is also our main inspiration. In fact, I'm going to tell you how we build significantly on their work. In some sense, many of the ideas are from their work and we strengthen them to get our result here. But both of these papers relate the approximate non-negative rank of the pattern matrix MF to the approximate non-negative degree of the function f. Okay. And these are really the objects that you think these are. Okay. I have not defined them, but basically approximate non-negative rank is the non-negative rank. So from a matrix, you're allowed to perturb any entry in infinity norm. So you're allowed to choose any matrix which is close in infinity norm to your matrix and choose minimum non-negative rank, choose a matrix which gives you minimum possible non-negative rank. That's the approximate non-negative rank. And similarly for the function f, again you are allowed infinity norm perturbations and you're allowed to choose the minimum function, minimum degree giving function to choose here. Anyway, so these papers relate the approximate non-negative rank of the pattern matrix to the approximate degree in basically the same way that we saw on the previous slide. Okay. And just like for us, their characterization is tight, okay, up to again the same constant factors, etc. So you could ask, well, they are also giving a tight characterization. What sort of is failing? The reason is that this approximate here's the definition. I guess I had it. The reason why this is failing for us is that this approximate non-negative rank of the matrix that we are looking at, the M cut matrix, which we are going to embed MF in, has actually a very small non-negative, approximate non-negative rank. So recall that the LP size was characterized by the non-negative rank, right? What would be really great is if even the approximate non-negative rank of the matrix we are looking at happens to be large, but unfortunately that's not true. Okay? In particular, it's not very hard to show that the approximate non-negative rank of the M cut matrix is just quasi-polynomial. Okay? So if you have any technique which lower bounds not just non-negative rank but the approximate non-negative rank, then you can never hope to prove a lower bound which is more than quasi-polynomial. This is really the place that both these papers would break down at. So both those papers will give you into the log n kind of lower bound on the CSP LP size, but they can't go beyond that because of this technical reason. And we basically get away, we break through basically this approximate versus exact non-negative rank business, and that's the reason like we can get the lower bounds we have. In particular, we also get an exponential separation between the approximate and exact non-negative ranks for some explicit matrix, which is really the M cut matrix, for example.
The bound on B, this is probably not typed, right?
Yes, that's a great question. Like, so you're asking, do we require
that B is larger than log?
Yes. So in the CSP kind of setting, it's sort of required. We're gonna see. So there are like two places where we are going to use this bound in. For pattern matrices, for some gadgets, it is reasonable that you can come up with a lifting theorem that works for much smaller B's. Okay, but for the kind, okay, but the form of the lifting theorem will have to differ. Okay, in particular, you cannot get some form which has some additive shift like this because for CSPs it's not true.
And another thing, for particular problems, so you said that you are allowed to choose the gadget as you wish.
Yes.
But for particular problems, it's not always the case, right?
That's a great question, but I'm going to show you that for every gadget G, the pattern matrix MF produced with that gadget, I can embed that in the matrix I'm looking at. So in some sense, any gadget would work fine for me. It's just that inner product would be particularly nice. So you're right that in general, it's not true that I can use any gadget for proving lower bounds. But for this specific task of proving non-negative rank lower bounds for CSPs, it doesn't make any difference.
CSP.
Yes.
Because you are in a general enough class.
It's sort of a technical reason, but that's I'll come back to all these questions. But it's for example, it won't hold for other problems, like it won't hold for clique or something like that. But it will hold for CSPs. And the reason is this. Okay, let me just explain to you. The reason is this. You can take a CSP instance on n variables. Okay, then you can take a larger set of variables and plant this instance on the larger set of variables by doing basically ignoring some large set of variables. Okay, this produces a valid instance of CSP. This is the reason why, in some sense, any gadget is okay.
So if you talk about other problems,
yeah.
So then there are gadgets that are okay. You know about gadgets that are okay.
Yes. So you can produce some reasonable gadgets, but we don't know how to analyze them. In particular, this gadget won't work there.
Okay. But you have gadgets that you can conjecture that you can generalize this result or that.
Yes. I mean, conjecture is okay. Yes. I mean, I can conjecture what lower bound one should be able to prove. I can also conjecture what gadget you should use, but I'm not sure of the specific form of the lifting theorem that you would be able to get with such gadgets. Okay. So
the reason
yes.
for the quasi-polynomial size like Johnson Linders is just why does it when you approximate? Why do you get quasi-polynomial? Why is the approximate rank upper bound so small?
The proof I know is through this communication model.
Because of unique communication model?
Yeah, like okay, so non-negative rank correspond or approximate non-negative rank. So the LP size etc. corresponds to there is a nice communication model that corresponds to it. So I think it is that Alice gets a cut, Bob gets a graph, and they want to communicate and measure the cut size in the graph, and they're allowed to use randomness, private randomness, and the random variable which their communication model computes should have expectation, which is the cut size. Okay, and then in this model, it turns out that the combination complexity in this model is related to, in fact, characterized by the approximate non-negative rank, and then you can give a simple protocol. So let's see if I can remember this.
You can just one guy samples a bunch of edges, and you send it to the other guy, and he looks how many of the edges are satisfied.
Inside the cut given to, yes,
So
yes.
Just a subset. It's just a sampling. Yeah.
But I think
Yes.
It's good enough.
Yes.
so by approximate rank you mean what's the
It's
error?
a Chow bound.
Yes, yes.
It's a Chow bound.
Yes, yes. This is approximate non-negative rank.
But what's the error that you know? I mean,
Yeah, what's the L infinity?
because
change?
because it's actually, I mean, the rank is polynomial if you want constant approximation.
I think here, let's see. I think it is sub-constant, but I don't exactly remember what's the exact perturbation here. Like it corresponds to the sub-constant kind of thing that you get in CLRS, like the error, and that's clearly that goes to 0, so it's sub-constant, but.
Because I think even in LRS we get better lower bounds in the approximate rank. Or I guess I don't know.
I mean, the parameter that's sort of unclear here is what's the error we allow, right? And okay, so for some choice of the error, it is quasi-polynomial, and I thought that that error corresponds to the error that CLRS gets. Okay. 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 So now let me just. So what I'm going to do now is the following. Okay, I'm going to show you some kind of an overview of the proof. Then I'm going to drop the slides and use the board. Okay. So great. So recall what our task was. Okay, we wanted to prove a LP size lower bound for the max cut problem. Using this Yannakakis theorem or the Farkas lemma, whatever, we can basically reduce it to lower bounding the non-negative rank of the M cut matrix that we defined. Okay. What we are going to prove is a lifting theorem, which would prove a non-negative rank lower bound on the pattern matrix MF. Okay. The way this is going to be useful to us is because we will be able to, for some choice of this small function f, I am going to embed this matrix MF inside this M cut matrix, which means that the non-negative rank lower bound on MF would imply a lower bound, non-negative rank lower bound on the M cut matrix. And in order to, so remember that our lifting theorem just gives a lower bound on the non-negative rank of MF in terms of the non-negative degree of the function f. So then I need to have a non-negative degree lower bound. This we are going to get at some point. The Sherali Adams has to come in, because we said that we are going to relate the Sherali Adams LP. It turns out that degree plus lower bounds are really equivalent to Sherali Adams lower bound. This I am going to explain to you in a minute. So with that chain of reasoning, it's enough to just lower bound the non-negative rank of the pattern matrix MF, and then our task would reduce to just proving the lifting theorem. We'll forget about the CSP application, and this is going to be accomplished via some tools. Okay, so it's sort of not important to mention the names even right now, because I'm going to do the details of it today. Okay, but that's our plan. So in the next part of the lecture, so basically I'm going to explain to you a couple simple points now, and then we are going to stop. That would be a natural point to take a break, and then after the break I would basically focus on proving the lifting theorem. Okay. So so basically let me sort of make this arrows clear before the break. Okay. Okay, so recall our definitions for linear programs for the max cut problem. So I hope all of you remember that we chose some linearizations, we chose some polytope, and the LP was basically the linearization, and the polytope we chose. Great. Now one way to understand LPs, and I'm basically using a dual characterization now, because this is nice to describe the Sherali Adams LP and the relationship to the non-negative degree. So I'm going to think of linear programs as giving dual certificates. What kind of a certificate is it? So a CS approximating LP tells me that the max cut in a graph G is at most C in size. In other words, it tells me that C minus cut G as a function over all possible cuts described by this vector x is always non-negative. Okay. So in other words, this whenever the LP proves to me that the max cut is at most C, it is proving to me that the function C minus cut G is always non-negative, right. So now we can try to understand what kind of proof is the LP giving us of this fact. It turns out that any LP can be thought of as giving us a proof which can be written in the following form. It expresses this function, this non-negative function C minus cut, as a non-negative linear combination of some fixed functions v1, v2, vr which are non-negative. Okay. In other words, for every LP you can find, so every LP is characterized by r non-negative functions over cuts, okay, such that for any instance G I can express the C minus cut function as a non-negative linear combination of v1, v2 up to vr. This r is really the size of the LP, okay. And this is really not hard to prove. So let me show you a proof so that everything is sort of clear. This is really simple. So remember what our LP was, right? The LP basically chose a linearization of cuts of graphs and gave us a polytope, right? So I'm going to tell you what these functions are right away. These functions are going to be so the AI is the ith row of A, okay. So it gives me some so it's the ith inequality in the LPP. For the ith inequality, I define the function vi as just this slack function of the inequality, bi minus ai or x tilde. X tilde, remember, is the linearization of x, okay. So these are functions, and I'm going to show you that in terms of these functions I get a proof of non-negativity of C minus the cut function, okay. So LP proves to me that the maximum cut in G is at most C, or the LP value is at most C. This means that C minus y in a product G tilde is the linearization of the graph G, is always non-negative for every y in the polytope, right. Now Farkas lemma says, so this is an inequality that holds for every y in the polytope. Farkas lemma says that any inequality that is true over all the polytope can be written as a non-negative linear combination of the defining inequalities of the polytope, okay. The defining inequalities of the polytope are that bi minus ai dot y is non-negative. So I can express this inequality, this non-negativity C minus y dot G tilde as a non-negative combination of the true inequalities, the defining inequalities of the polytope P, right. In particular, I can input y as the linearization x tilde of any cut x. That gives me that C minus x tilde G tilde equals some linear combination, non-negative linear combination of these functions vi, and by definition G tilde in a product x tilde is the cut value, because that's our definition of a linearization, okay. So in particular I have written the slack function C minus the cut value at any cut as a linear non-negative linear combination of these functions vi. Okay, is that clear? Like, this is really simple, but a good point to sort of understand. Okay, great. So any LP, so an R size LP basically corresponds to giving R non-negative functions, which gives you a certificate of non-negativity of this C minus cut function. Okay. So now we can ask, what is a Sherali Adams LP? What kind of certificate is Sherali Adams giving me? So it turns out that Sherali Adams corresponds to a degree D Sherali Adams, which is like an n to the d time algorithm, corresponds to giving a certificate of non-negativity for the C minus cut function in terms of d juntas or d monomials or d conjunctions, okay. So the v1, v2, vr are going to be just length at most d conjunctions, okay. In particular, a Sherali Adams lower bound means that this C minus cut function over any over some graph G naught has a large non-negative degree, okay. So in particular, this is the lower bound that is relevant to us. There is a lower bound due to Charikar, Makarichev and Makarichev, who showed that the non-negative degree of so this C is roughly close to 1, okay. So in this example, the optimal value is roughly half, and the LP value is close to 1, and this lower bound can be said as saying that the non-negative degree of roughly 1 minus the cut function is oh wow, this is n to the plus epsilon, okay, and it's larger than n to the epsilon. That really means that the Sherali Adams, to prove that the value is smaller than 1 minus epsilon, would need time at least 2 to the n to the epsilon, okay. and that is the LP lower bound, Sherali Adams LP lower bound that we are going to compose to give the lower bound on arbitrary LPs today. Okay. So that's the first. That's sort of the Sherali Adams aspect, and it tells you this. It basically tells you that the C minus cut function has large non-negative degree, right? Now in the next 10 minutes, I am going to show you why it's enough to prove a non-negative rank lower bound on the pattern matrix with this function. Okay, so this is the function I have a non-negative degree lower bound on. So then if my lifting theorem is true, I get a non-negative rank lower bound on the pattern matrix with this function. So what would be really nice if this function MF embeds inside MCut. This is what I promised you. So in the next 10 minutes, I'll show you that, and then in the remaining part, we'll just do the lifting theorem. Okay. So okay. Great. Okay, so remember this f is going to be some 1 minus epsilon minus the cut function of this graph G naught. So G naught is this hard instance for Sherali Adams, and we know a non-negative. Okay, and we know a non-negative degree lower bound on 1 minus epsilon minus the cut function. Okay, so here is the claim I want to make. Okay, so this G naught is a graph on n vertices. So in particular, this f is a function on plus minus 1 to the n to r plus. Okay. So so the embedding is really simple. Okay, for any alpha in sigma, I define a G encoding of alpha as as a string in C. Okay, and basically this is so at G alpha at beta. Oh, I am already using that. This is 0 1 to the b here. So for any gadget over b bit strings, and this is without loss of generality, it just helps in notation. Okay. So G encoding of alpha at beta is just going to be G applied to alpha comma beta. Okay. So this is just a notation. And now what do I need to tell you? For every, so I want to embed this matrix MFG inside the MCut matrix. Okay. So for every row and column of MFG, I have to find you a row and column of this m-cut matrix on n times sigma vertices. Okay? So, I am going to define the instance, and so mf is indexed by strings from sigma to the n, right. So, for every x and y which index the rows and columns of the mf matrix, I would find you a cut and a instance to look at. Huh?
The cut and a graph.
Cut and a graph to look at in the m-cut matrix. Okay. So, so for any y, I define the instance gy on sigma n variables.
Where does y live?
Y is in sigma to the n. So, 0 1 yeah, sigma to the n. So, I am taking the rows and column indices of mf g and trying to get a row and column of m cut. Okay. So, what I am really doing is the following. Okay. So, so look at, so I think of this input as n blocks of sigma each. Okay. And so this is my graph, and I want to use some x to tell me, sorry, I want to use some y to tell me what, as I told you, what I am going to do is take this hard instance g naught, okay, and plant it inside some vertices of this larger graph. Okay, so g naught is a graph on n vertices. Okay, so I need to find n vertices to plant this g naught on. So, the way I am going to do it is pick one vertex inside each block like this. This way I will get n vertices, and that would be my instance. Okay. So, this is some valid graph. Therefore, it and its optimal value is at most s. So, it does lie in it does lie in the indices of the rows of the m-cut matrix. So, this would be sensible, right? And this is going to be really simple. So, what variables should I plant it on? So, gy is obtained by planting g naught on C. So, in this I am going to choose, so y was an index in sigma. So, I am just going to choose G circle y. Let me just see.
Just the symbol that appears in the vector y.
Yeah, okay, yeah. So, y is a b bit string, so it will just be the symbol, yes. This would be just yi then. So, in this thing I would just use y1, here y2, and so on up to yn. Okay, so this tells me what n variables to plant my instance g naught on. Okay.
So, the other vertices will be disconnected
Yeah.
from the isolated.
Yeah, they belong to no edge. In fact, they appear in no edge. This is really the same as the random planting that happens in CLRS. Okay, so yeah, this is really old stuff still. Okay, and now what do I need to prove to you? That if I take any cut inside that indexes the m-cut matrix, then the cut at this gy graph is really the cut of the g naught at an appropriate. So cut of this should correspond to, sorry, the entry of mf should correspond to the cut of this graph gy. Right, that's.
Don't you need to tell us the encoding of a row?
That's what I said before. So for x, I will use. No,
X should then index a cut, right?
Yes, x should index a cut. I think it's like it defines some. So I don't need to. So all I need to prove is that that all cuts appear. So clearly, if I look at the M cut matrix, it's indexed by all possible cuts on these many sigma times n vertices. So all cuts appear there. All I need to show you is that if I compute, see, I'm getting a little bit confused.
There might be several cuts that correspond to the same.
That's okay. I just need to find a submatrix, right?
Yeah.
But then you
But you should be able to show us where this X.
Yes, yes. Let's see. So I think it has to be the simple thing. So if I take any x, then yeah, I think it's yeah. So it's x1 y1, x2 y2, and so on. Okay, basically I'm taking, so any cut is described by a plus minus 1 valued vector, plus 1 minus 1 valued vector for each of this sigma times n coordinates. I'm taking the coordinates corresponding to the vertices I planted on.
I think here you need to apply G.
You have to apply G. I mean, G was not yours. You have to G. So you want to be right. You want to say whether an element is in the S or not. Somehow a string and sigma.
Sorry. Yeah, yes, I think you're right. This has to be it. Let's see if this makes sense.
Yeah, you don't need the voice because I mean, you don't have the voice. Just remove the voice. I think that is correct.
Yes. Sorry about this. Let's see. You're saying this makes sense?
Yeah, because you will evaluate it on.
Okay. Yes. I think that's correct. So right. So x maps into this string. Instance maps into this gy, and now I need to compute what happens to the cut value here, like the function value. And that just equals c minus the function f applied to gx1 y1, gx2 y2, so on up to gxn yn. And by definition, this was equal to f of g applied to x1 y1, g applied to x2 y2, and so on. And that is the x comma y entry of my pattern matrix. This should be x tilde. Yeah, sorry, I got a little bit confused, but hope that makes sense. Okay, so what we've done so far, let's just summarize so that we can go to the lifting theorem. We wanted to prove LP lower bound. We reduce it to this non-negative rank of this M cut matrix. Then what we did is we found a function f such that the non-negative degree is large, like some n to the epsilon, and showed that MF embeds inside M cut, right? And all I need to do now is to show a rank plus lower bound on the MF matrix. Okay, and this we will do after a 5-minute break. Does it make sense? Does it look okay?
Can you write louder?
Can I write larger? Yes.
Okay,
Okay, great. So our goal now is to prove a lower bound on the non-negative rank of the MF matrix in terms of the degree, the non-negative degree of the function f. Okay, and let's just recall all the notation. Okay, so the MF looks like this. You have x, y, and x and y live in good, great. So let's see. So what we're going to do is work in the contrapositive. Okay, we're going to assume that MF has a small non-negative rank, and derive that the non-negative degree of the function f should be small. Okay. So let's say that the rank plus of MF is some small r. This is visible, right? Yeah. Okay. So let me just make some nice normalizations to aid calculations. So I'm going to when I write expectations, when I don't say about the distribution, it means that the distribution is uniform over the domain. So I'm going to normalize this to have expectation 1. So in other words, I make it a density. And similarly, I make the matrix have expectation. Okay, by rescaling or whatever. Okay, so now suppose the non-negative rank of MF is low. It's some small r. I want to somehow relate it to the degree of the function f. Okay, so what I'm going to show you. So I want to show somehow. So what does it mean to prove that f is of small non-negative degree? It means that f is a non-negative combination of d juntas. So let's just call these objects conical d juntas. Okay, so I want to show that f is a conical d junta, right? Assuming this for some d that relates to this r. Okay, so instead, what I'm going to show you is first that f is okay, and for d, this d would roughly look like log of the number r. Okay. So I'm going to show you that in some certain sense of approximation.
It's only one line with the big font, and then you are back to small font.
Oops. This is okay. Yeah, I'll write bigger now. Let's okay. Okay, so I'll first show you that so f is approximately a conical d junta. From here, I'll go to f. So f plus some shift okay. So those will be the two steps we will do. So let me define what approximate conical d junta means. Okay, so just two definitions before we get going. Okay, so first I'll define an epsilon decaying function. Okay, so I'll say that a Boolean function is epsilon decaying if expectation h is 0 and the Fourier coefficient at s of h decays exponentially in the size of s. Okay, great. Great. So now I'll say that f, or let me use maybe see L Yeah, it's like it's
Well, just as an example.
yes, yes. It's like so that would be in some sense a maximally bent function. So it would be maximally like this, but in some sense we are allowing some slack to ourselves here.
Just as an example for the definition, what
yes.
Does anybody know an epsilon decaying function?
Yes, yes. So the inner product function, as Avi said, is an example of a epsilon decaying function. But yeah, really in some sense it's a notion of what a small function looks like, or what something which is like what we would think of as close to 0 or whatever. Okay, and we'll say that L is an epsilon delta conical dihunta. This is our notion of approximation. If L can be written as okay, so this is somewhat of a mouthful, so let me explain that a bit. So these are going to be some non-negative scalars. These are conjunctions, our monomials. Okay. Now there are two sense. Okay, so if there was nothing, so if this part wasn't present, then this is what. So there are D conjunctions. Okay. So if none of this part was present, then it's an actual dihunta. It's a conical dihunta. Now I'm allowing two senses in which I'm approximate now. Okay. The first is that I allow a multiplicative 1 plus hi. Okay. So this hi is going to be epsilon decaying.
This is not CI evaluated
No.
No, it's fine.
Okay. Since I had this x here, yeah, maybe it was better without that. Okay, so this is a conjunction. I am multiplying it by 1 plus a epsilon decaying function. So this is some kind of a multiplicative error, and then this is going to be a additive error. Okay, so this is going to be a non-negative. So the gamma is going to be a non-negative function. Okay, and expectation of gamma is going to be less than delta. Okay, that's what I mean by a epsilon delta approximate dihunta. Okay, so in the first step, what I'm going to do is use the fact that the non-negative rank of MF is small, and obtain that F must be an epsilon delta conical dihunta for some values of epsilon and delta. Okay. So let's see, we can push this up a little bit. Okay, not the most efficient way to do it. Great. Okay, so here is the claim I am going to prove. So B is going to be more than log n here. For all F correctly normalize, some constant some constant. Let's call it beta. My alpha looks like 2, so let's make it beta. And D is going to be like some log of rank plus of MF. Okay, so I'm saying that if you take so I'm expressing a I'm saying that f must be an approximate conical D junta if the non-negative rank of MF is small. This is sort of an awkward way to put it, I guess, but basically imagine that the log suppose rank plus of MF is R, then log, so this D has to be like log R over B, and then I'm claiming that it's going to be 2 to the minus B over 2, so this, think of this as some epsilon, this is like epsilon to the D up to some constants, and then we are claiming that it's going to be epsilon versus epsilon to the D conical D junta, where D is like log R. So that's a good question, but basically D is parameterized here, so I can choose any D which is larger and make this error smaller.
I understand that that's what you mean, but if you want to say you can do it with D which is a small step, you can do it with D that is
Yeah, so I can do it for any D which is larger than this.
so you pick the smallest.
There is a different,
The question is, how would an approximate D junta do you need to get an exact D junta?
Oh, because D appears in the boundary.
Yeah.
Sorry, good.
Yeah, so we would have to sort of use this parameterization later on. Yes. Okay, great. And this part is fairly simple. So let me show it to you how we are going to do this. Okay, so and it would also sort of nicely play with what's going to come next and sort of the main crucial part. So suppose rank plus of MF is R. Okay, so what does that mean? It means that MF is some I from 1 through R of some MIs. These are non-negative rank 1, right? So since they are non-negative rank 1, I can write it as some lambda I Okay, so again I'm choosing a nice scaling to work with. I'm saying that for every rank 1 matrix, I write it as some scaling of ui times vi transposed. So these are just vectors over sigma to the n. And then I have scaled everything so that ui's and vi's are densities. In other words, as functions, their expectation, they're non-negative functions that have expectation 1 over the uniform distribution over their domains. Okay, so this I have done nothing so far. Now, so what's the idea? We basically want to look at each of the R rank 1 components and approximate each of them by an epsilon delta junta. Okay, and these rank 1 things are actually very well studied in communication complexity. They are in some sense just the analogues of rectangles. I mean, rectangles can be thought of as the case when ui's and vi's are uniform over a subset. Okay, and here in some sense it's a generalization. Any product, it's like a product distribution, which is really a rectangle. So what we will do is the following. Okay, we are going to do the communication complexity style argument. We're going to show that if we have a large rectangle, I'll define this in a moment. Then we'll do some heavy lifting. We'll show that large rectangles are nicely behaved in a certain way. Okay, so we'll show that. For this case, we'll use what I call as the junta approximation theorem. And for small rectangles, I would be okay to call them as error. In other words, absorb them into this epsilon to the d part, like the gamma part in my epsilon delta junta. Okay, so I would basically call them some errors. Okay. So a large rectangle. So in a rectangle world, I can define a large rectangle as in some subset sizes. Here I have distributions. So I'm going to use min entropy as my definition, or min entropy as my characterization of what a large rectangle means. Okay. Okay, so the mean entropy is just for the sake of definition here. So we'll say that U which is the density.
Yeah, one thing, don't forget the U's are not from sigma to the end.
Yes, sorry, yes, they are. They are, yes. Sigma to the n to r plus, expectation U is 1. Okay, so suppose I have a density like this. So it defines a random variable where the probability of the random variable x being some value x, small x, equals ux times sigma to the minus n. Okay, so that's the usual notion of density, and I define the min entropy h of the density u as see the max of log of sigma to the n upon u of x. But it should be min or max, let's see. Looks all right, I guess. Okay, so that's the usual notion of min entropy. Okay, good. So so my notion of large would be the following. Okay, so I need to specify what I mean by large rectangle. So yes, I guess I can call it B, right? And this t is roughly going to be like log of r. Okay, so I'm going to say that my rectangle or my rank 1 thing defined by ui and vi is corresponds to a large rectangle if it has if it is at most t blocks deficient in min entropy. Okay, and now the idea is the following. Okay, I'm going to show you a Hunta approximation theorem. So let's see, where should I write? So if I write on this board, it's visible, right? Okay. Okay. I also so let's maybe do it this way. So yeah, sorry, I forgot one important point. Okay, so now recall that I assume that the non-negative rank of MF is R. So I write MF as a sum of R rank 1 non-negative matrices. Now I want to somehow get some simpler representation for F. Okay. Now the entries of F appear in this matrix many times, right? So one way to get some simple representation of F is to average it out. Okay. So what I'm going to do is use the averaging of MF to give me some representation of F. Okay. So for any z, I define f of z. So this is just true. So this is the claim. So f of z equals expectation right? This is just true. I'm basically averaging over all entries such that the gadget's output on x and y gives me z, right? And for any entry that this happens, the entry in my matrix f of z, so this is just going to be true, right? Now I can use my low rank thing to write this as sum over I, lambda I, expectation okay. And now look at this function. Okay, what would be really great is the what my plan is the following. Okay, look at it for every rectangle corresponding to index I. I'm going to take this function and prove that it is an approximate junta, epsilon delta approximate junta, and then these are just non-negative coefficients. They are scalars. They don't depend on x or whatever. So this equation then will give me a junta representation for f, an approximate junta representation for f. Okay. So now I want to basically take any rectangle and understand what this looks like, right? So for any rectangle I define j u v. So now let's say u v are the densities defining your rectangle. I define j u v as a function. This is a legitimate function on +1 - 1 to the r. X y are such that g n x y equals z, expectation of u I x v I y. Okay, and now let's just try to understand what this function is, right? ui and vi's are positive urban densities, right? So in particular this juv function is non-negative. If I take the expectation of juv, then is the expectation over all possible xy uniformly drawn from their domains of ui x vi y, and since ui's and vi's were densities, this is just 1, right? So in other words, j is a non-negative function with expectation 1. In other words, j is a density. In fact, is the density of the random variable g to the n of xy. Okay. So this random variable g to the n of xy, when x and y are drawn uniformly from the rows and columns, takes values in +1 - 1 to the n, right? And juv is the density of it corresponding to So say when I use u's and v's as the distribution. Okay. So when I draw x and y from the distributions corresponding to u's and v, this juv gives me the density function or the distribution of the random variable g to the n of xy, right? Okay. And we want to understand how juv looks like, okay, when in terms of some properties of this rectangle u's and v's. Okay.
Why call it the juv?
Well, you mean why I chose notation j?
No, I mean, what's the relation between u and ui?
Sorry, there is no I here. Sorry. Yes, this is just a So we are going to apply this on every ui and vi there, but in general this is just about any densities u and v. Here. Yes. Okay. But let me just erase this anyway. I want to use this space. So juv is a density. Okay, and what we're going to show is that let me just use if I write here, is it visible? Whoa. Okay, so So basically what this is saying is that if I have u and v distribution that correspond to large rectangles, meaning that the densities correspond to distributions with high entropy, high mean entropy, then the density function g to the n applied to x y is approximately a conical d junta. Okay, and the approximate is in the sense that we defined earlier. Okay, so I'm going to spend most of the last 20 minutes or so on this part, but let me tell you how this fits in with the rest of the stuff. Okay, now what we will do is the following. Oh. Okay.
So the main stuff was getting it not to be approximate.
Oh, remember we are working in the contrapositive. We assumed a non-negative rank.
Yeah. This is still approximate. You need to get exact.
No. That part is actually the easy part. It's like most of the difficulty is in getting the error to be exponentially small in d. So this is where we sort of are making most of this is where most of the heavy lifting is happening. Okay, and going from here to exact thing is actually not that hard. It just follows from like standard hyperplane kind of arguments that CLRS also used. Okay, so let me just maybe make that point here. Okay, so let's look at the expression here. What we are going to do is for rectangles which correspond to high mean entropy, we are going to use this Junta approximation. Okay, for which are low entropy, they would correspond to error, and it would be easy to say that they are going to be small. This is just because if the distributions ui and vi are low mean entropy, then there is some point x or y where they take large values, right? But then lambda I times this function is destined to take small values everywhere. This is just because expectation of ui of x has to be expectation of mf, which is 1. Okay, but okay, so we have some normalization condition. This really means that pointwise for any ui or vi, lambda I times ui has to be at most 1. But if ui takes a large value, then lambda has to be really small. So which means that these rectangles really contribute like a small value. So we can just add them all up together and call them error. Okay, so then it's going to be enough to just work with large mean entropy rectangles and prove that they are the density function, or the JUE function is approximately a D junta. Okay, so that would give us the approximate D junta claim. Okay, going from here, maybe I can keep it here. So going from approximate conical D junta. So this would give us that f is some approximate D conical junta. From here, concluding that f plus some 1 over n is a whatever some 10D conical junta is not hard, and it uses standard kind of technology. Okay, so and then in some sense we are done, because we would have a lower bound on the conical junta degree of f plus 1 over n from the Sherali Adams stuff. So we'll be done, because this would be a contradiction. Okay, so so therefore all the remaining work in some sense is in showing this junta approximation theorem. Okay, so is the plan clear? Are there any questions before I can move ahead?
Not a question, but a comment. You probably want to, I mean, if anybody is in the dark about the mean entropy notation, I mean, this whatever you are proving is essentially the best possible, because one thing that a rectangle can do is just give information about the coordinates.
So I'm going to do those examples. Yes, that's yes. I'm going to spend time on that part now. Okay, so let me so let's see. So this I'm going to erase all of this board now. So our focus will be on proving the Junta approximation theorem from now on. Okay. Okay, great. Okay, so So before trying to prove, let's try to gain some intuition as Avi suggested right now. Okay. So recall our setup. U, V are densities on sigma to the n. Sigma is actually just 0, 1 to the b for us. We are going to use the inner product gadget. So like G is fixed, and this b is whatever larger than log n. Okay, and that sort of won't be important for this thing. But let's take some examples of densities with high min entropy and see in some sense why we even expect this JUV2 to be like a D-Hunter, right? So first example is really simple. Suppose UV is uniform sigma to the n. Okay. Then what's the distribution of the random variable g to the n xy? Yes, it's a constant. Does everybody see why it's a constant? So here, like x is drawn from the distribution given by u, and y is drawn from the distribution given by v. Okay. So then, yes, because g into the n of xy is a uniform distribution, because x and y were uniform. Here, in some sense, you don't even need that g is an inner product. By the way, any balanced function is enough here. Okay. And then JUV is just a constant. Okay. Great. So let's take a somewhat non-trivial example. Suppose UV are suppose UV are distributions which look like this. Okay. So there are some T blocks which are fixed. So same T blocks are fixed, and over the rest the distribution is, let's say, uniform. Okay. Now what do you expect to happen? So if I apply g to the n to the coordinates in these T blocks, I'll get a fixed value because the x restricted to this T coordinates and the y restricted to T coordinates is fixed. So g to the n restricted to the first T coordinates is fixed. So in the output g to the n of xy, the first T coordinates are fixed, right? And the rest is uniform. So it's the previous argument that we did. So here you're going to get uniform, right? Now, what does JUV look like in this case? So JUV is a density function, right? Clearly, so look at any z such that the z's first T coordinates do not match the T coordinates obtained by applying g to the n to these fixed parts. Okay. Then there the density function has to be 0 because that point cannot appear in my distribution. So all, and in other words, and whenever it is equal to the first T blocks, it has to be equal over all such points where the first T blocks are the correct T blocks. So in other words, all the density function has to do is to check if the first T blocks match the fixed output that I need to obtain, right? So it is a T-Hunter because it only cares about T coordinates, right? And let's take a slightly more complicated example, and then we will go to the general case. So now suppose u and v are like this. So they have first T blocks fixed. Okay. Now rest of the things over different blocks they are uniform. Okay. But inside each block, so over different blocks they are independent, but inside each block they are not uniform, but they are some distribution with high min entropy. Okay. So for every block here, let's say the min entropy of this block is 0.9 times b, let's say, right? So it's a b bit block. So the maximum possible entropy is b, and I'm saying that in each block I have entropy at least 0.9 times b, and over the blocks my distributions are independent. Okay. Now what do you expect to happen? So the first T blocks, the reasoning has to be the same. They are going to be fixed, but now I'm not uniform here, but I apply g to the n, and here is where g being an inner product actually matters. Okay. The idea is this, and in some sense now I am preaching to the choir here. I am applying g to the n, which is a strong two-source extractor, to distributions which are blockwise high min entropy, right? So look at any corresponding blocks. They have 0.9 b entropy. I am applying g to the n to the pair of them. So now I know that if I take two distributions with high min entropy and apply two-source extractor to them, then the output is going to be close to uniform. Okay. So even in this case, my distribution, the output distribution, should look like T blocks fixed here, and then some close to uniform here. Okay. So in other words, I should get some approximate T junta again. Okay. And really what I'm going to show you is that this is all that can happen. Okay. So let me tell you how I'm going to prove the junta approximation in general. This is the intuition.
The main problem is independence, right? I mean, you assume independence across.
Yes. So I'm going to basically define a slight relaxation of this independence property that allows me to still sort of obtain the same kind of conclusion. And yeah, so and then then we go from there. So let's be a bit quick, I guess. Okay. So now let me generalize, as Avi pointed out. I don't want to use independence across blocks, so I want to introduce some kind of relaxation of this property. Okay. So I'm going to define blockwise dense distributions or densities. So I say that U is blockwise dense if for all blocks I, the n small n blocks now. Yes. Okay. So if over all blocks I, the mean entropy of the distribution restricted to the coordinates in I is close to its maximum possible mean entropy. Okay. So this is my relaxation of the notion of uniformity. Now I want, so this sort of is the relaxation of the first example, or sorry, the second example. Now I want to also allow T fixed blocks. So I'm going to generalize it to T conjunctive blockwise dense distributions, and I'll say that U is T CBD, or I'll say D CBD if for all, so okay, so if there exists I less than equal to D such that Ui is fixed and Un minus I is blockwise dense. Okay, so this is really the generalization of what we had for the third example. Okay, and now I need, and by the way, both these definitions and these ideas were present in this Mika Goose et al. Paper that I mentioned before. Okay. But now we are going to introduce one somewhat more refined version of this that's going to be useful to us. Okay, so far things were about a single distribution. Now I'm going to have a pair of distributions UV. Okay, I'm going to say that they are aligned DCBD if first of all they are individually DCBDs and their aligned blocks match. Sorry, their fixed blocks are aligned. Yes. Okay, and notice that this is a somewhat of a non-trivial notion. So at first you could expect that I could take any DCBD distributions and maybe take the union of blocks to make them align artificially. But this is problematic because you know, now you have sort of added more blocks than one of them was aligned at. So now you have to sort of fix those blocks, and now once you fix those blocks, you have to take union. The union becomes larger, so you can spiral out like this. So just so in some sense, this is not just a union. You can't sort of hope to, or at least immediately speaking, you can't hope to do this just by taking union of the fixed blocks of the individual UNV here. Okay. So what I am going to show you now is the following. So let me maybe erase these examples.
Would it work for more than two densities?
Say it again.
Would it work for more than two densities?
Why not?
Yeah, I mean the definition would.
So it
Yeah, I'll tell you what. Well, I'll tell you what won't work, or at least what I don't know how to make it work. And yeah, I also don't know a use for it right now. Yes, but what I'm going to show is the following decomposition lemma. Yes, yes, precisely. So we're gonna show that. So the hypothesis is the same as the Hunter approximation. We're gonna show that then. So maybe let me just remind you that uv h infinity okay then. So as we said, the product distribution defined by u and v is going to be a convex combination of aligned DCBD distributions. Okay, that's sort of the claim I want to make. So in particular, I want to write that u product v equals some lambda I ui product vi plus some error, such that this is really a convex combination. Each of the individual components are aligned DCBD distributions. Okay, and then this D is going to look like whatever is the entropy deficiency. Okay, and lambda error is exponentially small. Okay, and given this, proving the Hunter approximation theorem is not that hard. Okay, so all you sort of now need to do is to check if the extractor property holds not just if things were independent across blocks, but also holds even if you were blockwise dense, and that happens to be true. Okay, and that's sort of not that hard to verify. So I'm going to ignore that part. But really, if you have this, then you are done. Like you get the Hunter approximation theorem just from this decomposition theorem. Yes, you're asking where.
When you're doing the Hunter approximation of blockwise.
Yes, 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 yes. So that goes into this property of the extractor. So let me make like a short 1 minute comment about that. So when we applied G to the n, so when we applied the gadget G to blocks which were independent, then the distribution you get is close to uniform and independent across blocks. Okay, but now you have blockwise dense, so there is maybe some minor, but still there is a dependence across blocks. You can ask what happens to the output distribution. Okay, what you can prove is the density of G to the n applied to x and y when x and y are blockwise dense instead of blockwise uniform is now going to be an epsilon decaying function instead of a constant function or close to constant function. Okay, and so this epsilon decaying comes just from the extractor property. Okay, and okay, so I'm not going to elaborate more on that. I'm basically going to focus on this decomposition theorem, and at least roughly you see how this decomposition theorem will give the Hunter approximation, because each of these UIV are aligned blockwise, aligned CBD. So for the aligned blocks you get the Hunter. For the non-aligned part, you're blockwise dense. So when extractor is applied, you get some 1 plus an epsilon decaying function. So that's the multiplicative part that you get multiplied in the Hunter in the epsilon delta Hunter definition. Okay. And then finally, you have this error part that gives you the additive error, and it's going to be exponentially small in the degree. Okay?
There are similar things like this in the extractor literature, the decompositions of this type.
So for example, go on.
I'll show you later. But
yeah.
Anyway, you didn't.
But yeah. So in some sense,
not with the definition of blockwise dense.
Yes.
You want some fixed components and other.
Yes. No, it's possible that a generalization to some other sort of notion would actually help. But yeah, let's talk about that in a few minutes. Let me just complete some ways to.
Nobody will. You can finish what you want.
Okay, great. So I want to prove this decomposition lemma. Okay. So I want to take this product distribution defined by U and V, decompose into a convex combination of aligned CBD distributions, and then some small error. Okay. So I'm going to do this in some sense the most trivial way possible. Okay, I'm going to give you an algorithm to do this. It will take input this u's and v's and give me this decomposition. Okay, the analysis of this algorithm is of course the tricky part, but I guess we will not get to it. But the algorithm I can show you right away. Yes, save 5 minutes. Okay, so you have let's see. So you have so suppose you have a, so I'm thinking of mu as the joint density, the joint product density u and v now. Okay, you are promised that the min entropy is t blocks short of whatever it is supposed to be. So this is no, this is correct, I think. So it is some t short of whatever is the maximum min entropy, right? So it is like close to being high entropy. So what I'm going to do is the following. Okay, so it's somewhat dense, but let's see. So I'm going to describe a algorithm which will take input a rectangle. Okay, so in the beginning my rectangle is really simple. It's going to be just sigma to the n cross sigma to the n. Okay, it will take some f which will be the fixed blocks. Okay, so in the course of my algorithm, I will some iteratively fix some blocks of my distribution. In the beginning again f is going to be empty. Okay, so now what I do is the following. I take this rectangle defined by the product AB. So this is going to be sigma to the n in the beginning. Okay, and okay, so so ignore this part for now, or maybe let me use this. Okay, great. Okay, so look at the random variables defined by the density. So imagine the rectangle in the beginning R is just the sigma to the n cross sigma to the n. So this mu subject to R is just the total density, the product density u times v. You take the random variable x comma y sample from this distribution, right? Now if x and y are already individually blockwise dense, then I'm done. Okay, because I don't need to align or whatever, you know, they are blockwise dense, so the aligned blocks are empty and they're already aligned already, right? Great. So this case is easy, so I'll just terminate, right? Otherwise, if one of them, at least one of them is not blockwise dense, then there must be some blocks where the min entropy is not not large enough, right? So there must be some block, and if the min entropy is not large enough, there must be some assignment to the variables in that block such that this assignment is more probable than it should have been. So in other words, the probability that, let's say, the x projected to this block S takes the value alpha is larger than some sigma to the minus 0.8 times S. Okay, this corresponds to some 0.8 B entropy condition that we wrote before. Okay, S is the set of blocks I found. Yeah, so S is the set of blocks where the min entropy is not as large. So there must be some assignment to these blocks which is more likely than it should have been. So I just find some such thing. Okay, and what I'm going to do is really simple. Okay, I'm going to just fix the distribution on those blocks. Okay, so that block was that block of variables had some assignment which was too likely. So I'm going to fix that assignment. Okay, so I'm going to take so this was on x part. So A was the x part of the rectangle. I'm going to fix this. So I'm going to split this rectangle into parts where over the blocks S the assignment is alpha, and over the rest where the assignment is not alpha. Because I have split the rectangle into two parts now. Now look at this new rectangle. This new rectangle obtained is where S part is alpha and B part is the same. Okay. In the beginning their fixed blocks were aligned, but now I have fixed more blocks here, so they are not aligned. So what's the way to fix this? Again, I'm going to do a trivial thing. I'm going to basically recurse on B now, take all possible assignments to the blocks in S, and make new rectangles for each possible assignment. Okay, so let me maybe draw the. It's maybe nice to see the tree that we are going to form. Okay, so in the beginning we have this sigma to the n by sigma to the n rectangle.
Maybe the algorithm is actually a communication complexity algorithm.
Yes,
so
yes.
You want to the stress this, that they operate, I mean, they arrive at some rectangle, God knows how we got this rectangle.
Yes.
As part of the communication, like of the non-negative range decomposition.
Yes.
And now they look at their inputs and they continue sending bits to each other in order to refine their.
Actually, yes, it is. Yeah, in terms of a protocol, I guess it's very nice. But there is some subtlety here. So let me point it out. Like the tree doesn't just grow in depth, but also grows sideways. That's sort of the subtlety here. So let me explain what I mean by that. Okay. So you start from this full rectangle. Okay. Now let's say you found that some assignment to some blocks in the x part was too likely. Okay. So you fix. So this is, let's say, A. This is B. So you fix A over S to some alpha B, and now you continue sideways on the remaining rectangle. Okay, so now you make, so this is some new node. You make a new node for A, S not equal to alpha, and B.
So what do you mean sideways? This is a standard communication, like Alice tells Bobby whether value is alpha or not.
Yes.
That's what you did.
No, but now I'm going to continue this way. So I'm going to keep recursing on this direction, and I'm also going to recurse in this direction. Like that, now two things will happen now. Okay. So let's discuss this thread in a moment. But what happens now is this: I have now this doesn't satisfy my invariant. Okay. So now I have to recurse on the B part. So now I just basically take all possible fixings of the B part. B given S equals beta 1, B given S equals beta 2, and so on. Okay, so I form many new nodes like this, right? And the invariant satisfied by these nodes now is that their fixed blocks are aligned. Okay, and now here this was a rectangle which I hadn't fixed any blocks, or at least there were the blocks are unconstrained still. So now on this I again recurse. So I basically find out if there is some assignment to x or y which is more likely than it should be, and continue.
So what's wrong with the communication complexity? I mean, Alice tells Bob whether I mean, she looks for a high probability input, for a very high probability input, and
Yes.
tells Bob whether she has it or not.
Yes.
That's a split of her input.
Yes.
And then Bob, in the first case, splits, immediately tells the value he has in this
Yes.
set of coordinates.
Yes.
And in the other case, they proceed.
I guess yes. This sideways thing is natural in the communication. Yeah, you're right. Yeah, actually, yes. Yes. So it's a nice
You don't
simple.
have to think of it as, I mean, it's an algorithm, but
Yes.
the algorithm proceeds by the players fixing their input
Yes.
successively.
Yes.
And what you want to argue is that they will not go on for too long, because
Yes.
each time they fix a high probability input.
Yes. There is also one other. Yeah, but so let me just complete what's going to go on here. Now this process will continue until at some point either your rectangle, the distribution restricted to some rectangle here, let's say A prime, B prime. So over all this layer, the invariant is that the fixed blocks are always aligned. Okay. So if I get a distribution which is blockwise dense on the unfixed part, I'm done, right? So either I would end up with blockwise dense distribution, in which case I terminate this sideways, or I get a rectangle. I get that the measure of this rectangle with respect to distribution is too tiny, and I just call it error and be done. Okay. Okay. Now on this part, I will continue doing this process iteratively. So again, like after I have branched out on all possible values for the blocks S in the B part, again the invariant that the fixed blocks are aligned is satisfied. So now I can ask if they are blockwise dense, because if they are, then I'm done. Otherwise, I continue going deeper. Okay. So now at some point I will hit depth D, which was my target, right? Now at this point, if there is some rectangle which is not blockwise dense already, like on the unfixed parts, then I'm going to declare it as some other kind of error. Okay. So I'm not going to go deeper than the depth D that I have targeted myself. So otherwise, I'm going to say error here.
But this cannot happen too often, because the measure of
Min
is
entropy.
small because of the initial min entropy.
Yes, but that's sort of the tricky part. I mean, that's the intuition. but analyzing that there are not too many deep paths, like the measure of the leaves that correspond to bad paths is small, is the most tricky part of the argument.
Because of the definition of why is density.
Yes, yes, precisely. Like it's so one of the paths. So the measure of measure of any leaf is small by the argument you just said, that the min entropy was large in the beginning, so I can't have done it for too long. But to show that when you add all the leaves with bad paths together, the measure is still small is the tricky part. Okay, this part is easy. That if you go to too small, the errors you add is not going to blow up, because for every layer you just have some error that you incur, and there are some d layers, so you incur d times that error. Okay, so that's not a big deal. The tricky part of the argument is to show that these too deep paths account for low error. And okay, so that's the tricky part of the argument that I'm not going to get into right now. But the point I want to impress upon you, as Avi mentioned, is that this is like a really, in some sense, the most trivial protocol or algorithm you would come up with for satisfying, for getting a decomposition if you don't have such a decomposition, right? Like in some sense, it's the most natural thing to do. So in some sense, we are not analyzing some clever algorithm. It's just the analysis is tricky, but the algorithm is really simple. In fact, a more or less a similar algorithm is present with up to some details in the GLMWZ paper. They didn't analyze it in some sense in the tightest way possible, and in some sense the most the technical core of the thing, in the main sort of core lemma is to analyze this simple tree decomposition in a tight way. And if you do it right, then you get this exponentially small error that you require. So it's sort of easy to get 2 to the minus b error here. That's sort of a simple argument. The 2 to the minus bd is what the tricky part is, and you really need the exponentially decaying error here to get the CSP application. Okay, that's it. That's what I had planned.